this chapter, we will be looking at various types of functions. In this lesson, we will be looking at synthetic division and the remainder theorem.
So one of the things that we're trying to work towards here is a method of factoring larger polynomials than just quadratics. Okay, you spent the last couple of years working primarily with quadratics and learning how to factor those, and that's been really good. Now we want to start to take your ability to factor a little bit further here. And the way we do that is to kind of revisit this idea of division. Okay, we're going to learn how to divide polynomials. Okay, one polynomial function by another polynomial function. And in this course, we're going to look at two different methods. Okay, long division and then synthetic division. Okay, now we'll get to synthetic division here in just a little bit. Here, we're going to start with long division. And the point here is that long division, polynomial long division, is very, very similar to just regular long division that you would have learned a long time ago here. So let's just take a quick look at this problem here. Okay, so here's our division symbol, here's our dividend, and here's our divisor. Now we're going to plot the quotient up front here. And now remember the way we do this here. What we're trying to do here is to basically eliminate, if you want to think of it this way, what we're trying to do here is we're trying to get rid of these values up here, the highest place value in these numbers here to start off with, as much as we can. But we're trying to knock down this number as much as we can, as quickly as we can here. So we're going to start with that first digit there, 3, and we're going to divide it by our divisor here. Now 3 divided by 3, that works out perfectly. We put a 1 here. Now I need to do this. I need to actually do this division here. So 1 multiplied by 3. And then I'm going to subtract. Now 3 minus 3 is 0. Perfect. So put a 0 down. And I'm going to bring down the remaining digits. And then the procedure starts again. Now, this time I'm looking at that first digit. And I'm going to ask myself, okay, 6 divided by 3 here. Okay, what's the quotient there? Well, 2. So 2 multiplied by 3 is 6. And when I subtract that, those digits there, I get 0, and then I bring down the 5, and I continue this here. Okay, 5 divided by 3 is just going to be 1 multiplied by 3, and then you subtract, and the value that you're left with here, this is your remainder. Okay, now back when you were learning long division, okay, you were working with the remainder here, and then your teacher would have shown you, you can keep going if you drop a decimal there, and then continue to bring down zeros as those placeholders there. And that was great, and you kind of felt empowered to keep going. You could kind of divide whatever you wanted. For us right now, actually, we want to stop here with the remainder. We're actually quite pleased with that. And now, when it's long division like this, you know you're done when the remainder here is a value that's smaller than your divisor. And we're going to have a parallel idea come out when we move into polynomial long division. We're going to do an example of that in a bit. Because really, to see polynomial long division, it's one thing to explain it, it's another thing to kind of do it. And so we're just going to jump in and start doing some examples here. But before we get to that, we're going to talk a little bit here about representation. Okay, so the result of dividing a polynomial by a binomial, x minus a, okay, where a is an element of the integers. We're gonna kind of focus on those kind of values at this point in time, and this will be explored in more detail later on in your education. But for right now, we're just going to look at where a is an integer, and it can be written using this division statement. Okay, so here's p of x. We're going to divide it by x minus a, our binomial. This is our divisor, and you get a quotient plus the remainder divided by that divisor there as well. I mean, if you were going to keep going, this division statement here gets you the quotient, and it spits out the remainder. Now, ideally, what you would do is you would divide the remainder if you could. Okay, like up here, I could keep going by dropping the decimal down. Okay, I would continue to divide that 2 by the 3. All this is saying right here is that what I would normally do is once I get the remainder, I would continue to do the division. Another way of writing that would be down here. And what you would do here is you would say that your dividend here is going to equal your divisor multiplied by your quotient plus your remainder. Okay, and that's what this is saying here written out in words here. But just to illustrate how that works here, if we go back to our previous example here, just to illustrate, our divisor, sorry, our dividend here was 365. Our divisor was 3, our quotient was 121, and our remainder was 2. Now, if this is a true statement, then it should be the case here that if I take 3 times 121 and add 2 to it, I should get 365. And I do. Okay? So this statement here is a true statement, and it's one that we're going to use in a little bit. Okay? We're throwing it down now because we're going to start to talk about division. We're going to start to talk about this pattern here, and we're going to talk about the form of writing our answer here. But we're going to see in a little while here that it's this form right here that's going to allow us, okay, to find a rule that we're then going to use to factor larger polynomials. And we'll see this in a bit. To start off with, though, we're going to take a quick look at examples of polynomial long division.
Write the division statement for the following polynomial long division.
So before jumping into an example of doing polynomial long division ourselves here, we're going to take a look at one that's already been done. So in this case, the dividend was x squared minus 4x minus 24. Our divisor was x plus 3. Now, what we're trying to accomplish with polynomial long division is we're trying to eliminate the highest degree term in the divisor in a step-by-step basis here, okay? So the highest degree term was x squared. I want to create an x squared with my divisor here and a value in the quotient. Now, what would I have to multiply by x to create an x squared? Well, I'd have to multiply it by an x. Okay, and what I do here is I'm going to line up the x term over the x in the dividend. Sorry, yeah, the dividend here. When you multiply this out, just like we did in the example here with the numbers, we take this and we multiply it through. But you multiply it by the whole divisor here. So x times x plus 3 is x squared plus 3x. And then you subtract. X squared minus x squared, okay, well, that goes away. Which is exactly what I wanted. Now I have to clean up what the 3x here, what this little 3 does here. A lot of times the mistake that people make here is they simply multiply this x by this x here. They forget about the 3 in the divisor. They treat it like it was just that. You got to use the whole divisor here. Now negative 4 minus 3x is going to be negative 7x. And then the rest of the dividend comes down. And then we start again. We're going to take and divide negative 7x minus 24 by x plus 3. And again, my goal is to remove the largest degree term. Now I can do that still because the degree of the divisor and the degree of the remainder are the same here. So if I just pick my the negative 7 up here so that when I multiply it out, I get the same coefficient. And remember, you multiply the negative 7 by the 3, and we're going to get negative 21. And then we subtract. Again, our largest degree term disappears. Negative 24 minus negative 21 is negative 3. So there's my remainder. And now we can actually do what the question's saying. Now that we've kind of walked through this procedure here, here's my quotient, there's my remainder. Okay, so our division statement would look something like this. We would say that x squared minus 4x minus 24 divided by x plus 3 is equal to, here's our quotient, plus our remainder over, oh, I'm sorry, whoa, I can't believe I did that. I don't know. I glanced right there and just copied that off over here. That's going to be over x plus 3. So negative 3, that's not a very good 3 there. Negative 3 over x plus 3. I could even change that to a negative right there and make this instead negative 3 over x plus 3. Now another way I could write this would be x squared minus 4x minus 24. Now I'm going to multiply this whole expression through by x plus 3. So it'll be x plus 3 times x minus 7. There's my quotient. And then my remainder is tacked on at the end there, that minus 3. So here's another way of writing that. And we're going to find that this is actually pretty useful. Okay.
Use long division to determine the remainder when 2x cubed minus 4x squared plus 3x minus 6 is divided by x plus 1.
So here's a question we're going to walk through the long division together with. So x plus 1, there's our divisor. Our dividend is 2x cubed minus 4x squared plus 3x minus 6. Okay, Now, to start this off here, the first thing I want to do is eliminate the highest degree term in my dividend, that 2x cubed. I've got an x in my divisor. If I multiply x by 2x squared, and I'm going to line that up right here. I'm going to make this 2x squared here. If I do that, then I can write 2x cubed underneath here. Now I still have to multiply the 2x squared by the plus 1. So I'm going to get plus 2x squared. But that's okay. I'm going to subtract this, and I know that the first term is going to go away, which is exactly what I want to do. I want to eliminate the highest degree term. And now, negative 4x squared minus 2x squared will give me negative 6x squared plus 3x minus 6. Okay, because I'm going to bring down the remaining part of the dividend. And then it starts again. I've got a negative 6x squared. I want to divide by this divisor right here, and I'm going to use this x here to try to eliminate this negative 6x squared. And I can do that by multiplying by negative 6x. So if I multiply that by x, I will get negative 6x squared. Then you still got to multiply the negative 6x by 1, so it'll be minus 6x. And then we subtract. Now there's a whole bunch of negative signs here, so be really careful with this. Okay, the first term should disappear, and it does, and that's exactly what we wanted. And now we've got 3x minus negative 6x. Now be careful with that, that's 9x. And then bring down the negative 6. 3 minus negative 6. Okay, the minus the negative means I'm going to add that value. There's my 9x. The degree of my remainder here is the same as my divisor, so I keep going. Okay, I keep going until this is a smaller degree than my divisor. Okay, and again, I look at the leading term in my dividend here, compare that to my divisor, and I'm going to want to put a plus 9 up there. So when I multiply that out, I will get 9x plus 9. And when I subtract, I'm going to eliminate the largest degree term here, that 9x, and then I'm going to get negative 6 minus 9, positive 9, negative 15. So there's my remainder. Okay, my quotient is 2x squared minus 6x plus 9, and I've got a remainder of negative 15. Okay, so the question says use long division to determine the remainder. Okay, well my remainder is negative 15.
Divide the polynomial 9x plus 4x cubed minus 12 by x plus 2, and express the result in the form px over x minus a is equal to the q of x plus r divided by x minus a.
Okay, well, there should be something about this question that jumps out at you right away. Okay, before we even jump into the division here, I'll maybe zoom in just a little bit. Look at the question here. Look at my dividend. My divisor's fine. X plus 2, that's great. Look at my dividend here. 9x plus 4x cubed minus 12. Whoa, I don't like that at all. It's written in the wrong order. I want to put the highest degree term first, and then have them go down in terms of dropping degree. Okay, so that's much better. Okay, I'm making the question look pretty. There's something about it that didn't look quite right. That looks pretty. Now I'm going to set this thing up for the long division. So I'm going to put my divisor out here, x plus 2. I don't know why I wanted to write something other than 2 there, but anyway. And my dividend here is going to be 4x cubed. Now, before I keep going here, I'm going to end up doing some subtraction. I know that. And I know that I'm going to eliminate the terms, highest degree term at first and so on. But there's a gap here. There's actually a 0x squared here, and then the 9x minus 12. I want to make sure that I have a representative of each degree of term. Now, the reason for that is so that I don't make a goofy mistake with my addition. I've got something that is basically a placeholder. Okay, I'm less likely to inadvertently subtract a squared term from just x by itself if I've got a placeholder there. So now I'm going to start my division. I need to get rid of this highest degree here term first, and this is what I have to work with. Okay, if I multiply x by 4x squared, I will get 4x cubed. And then when you multiply 4x squared by 2, you'll get 8x squared. and now I subtract. That highest degree term is going to disappear, and I got to be careful with this. I got 0x squared minus 8x squared. That's negative 8x squared. And then you bring down the remaining terms. Okay? Now, I start again. I need to get rid of the negative 8x squared. This is what I got to work with. Okay, if I multiply x by negative 8x, I will get negative 8x squared. But then I got to multiply it by the 2, so I'm going to get negative 16x, and then I'll subtract. And I know that the leading term here, the highest degree terms are going to cancel, but I get 9 minus negative 16. 9 minus negative, it's going to be 9 plus 16, it's going to be 25x minus 12. And I start again. Now the degrees are the same, so I know I keep going here. What do I want to multiply by x to get 25x? Well, it's got to be 25. So this will be multiplied by 25. So 25x plus 50. And when you subtract that, now I'm kind of running into the next question here, but that's okay. When you subtract that, negative 12 minus 50, that's going to be minus 62. And there's my remainder. And now my remainder has a smaller degree than my divisor, so I know that I'm done. Now I can write the answer in the form that they're looking for here. Okay, I take my dividend, and this time I'm not going to worry about writing the 0x squared because I'm done the division, so I'm just going to write the terms that are significant over my divisor, x plus 2, will equal my quotient. Well, my quotient was 4x squared minus 8x plus 25. 4x squared minus 8x plus 25 plus my remainder, which in this case was negative 62, over x plus 2, my divisor. Okay, now, I would be tempted though, however, to move that negative down out front. So make this minus positive 62 over x plus 2. That's probably a more popular way to write that. But anyway, that's what we're looking for in this particular problem.
Now we're going to introduce the idea of synthetic division.
All right. Now we're going to introduce this idea of synthetic division. Okay? And what synthetic division is, it's a short form of division, like it says here, that only uses the coefficients. Essentially, when you come back up here, I threw in a placeholder right here. Okay? Now, because I'm going to throw in a placeholder, when I see that there are 4 terms here, I would already know, if you just told me that I was going to use placeholders and that I had a polynomial that had 4 terms in it, I would guess there that it was a 3rd degree, it was a cubic, because this is going to be cubic, the second term is going to be quadratic, linear, constant. So the 4, really, all I really need to do to identify this polynomial is list the coefficients, the values in front that are responsible for kind of stretching and manipulating the function here. So 4, 0, 9, negative 12 is really all I need. Those numbers as identify the polynomial, as long as I know that the 4 is associated with the x cubed, the 0 with the x squared, and so on. Well, that's really what synthetic division does. Okay, the operations that we apply are applied to the coefficients, and so we're just going to do the division on the coefficients. Okay, which makes it kind of quick and easy here. But in this case here, we're going to be, you got to note this here, is that we are dividing. Okay, we are dividing by x minus a. Okay, we're dividing by just a simple little binomial. That's what makes this work. If you divide by something a little bit more complicated than that, it doesn't work very well. It's got to be in this form right here, where specifically where the leading coefficient here of the x is 1. That's the best way to do this.
Use synthetic division to determine the remainder for each of the following. X cubed plus 7x squared minus 3x plus 4 divided by x minus 2.
Okay, so here we go. We're going to start, and we're going to divide this using synthetic division. And what I'm going to do with these is I'm going to show you 2 different ways of setting it up. Now, they're very, very closely related. You don't even have to know both of them, but I just want you to be aware that there are 2 ways of dealing with this. First of all, I am dividing by x minus 2. Now, one way of approaching this problem is to think of it like this, everybody. What number here makes this equal to 0? Makes my divisor equivalent to 0? Well, the answer is 2. So I would put down a 2 here, a positive 2. Okay, this is one way of dealing with it. Then what I'm going to do is I'm going to draw myself a little box. Okay? Now, the way the box works here, there should be room for two rows of numbers. And then there should be room for a row of numbers underneath here. In the top row of numbers here, I'm going to list off the coefficients of the polynomial that I'm working with here. So 1x cubed, 7x squared, negative 3x, positive 4. There's my coefficients here. Outside the box again, what I've done is I've taken the number that makes this equal to 0, so positive 2. Now, here's the procedure for synthetic division. I'm going to bring down the 1. Okay, and then I'm going to multiply 2 by 1. So 2 times 1 is 2. And what you do is you put the 2 here. And then I add. Okay, and then I'm going to add. So 7 plus 2, 9. Then you multiply. 2 times 9 is 18. And you add these two numbers. Negative 3 and 18 is 15. 2 times 15 is 30. I put the 30 here, and then I add, and I get 34. Now, there we go. This right here is my remainder, and this is my constant term. And then if you think this through going backwards here, constant, linear, quadratic. So the answer here is my quotient, if you will, is going to be 1x squared plus 9x plus 15, and then there's a remainder of 34. Okay, now that's one way of handling this. Another way of handling this is to go back up to our problem here, and when you look at x minus 2, if the first thing that kind of jumps out here is that you see a minus 2, well, what you can do here is put a minus 2 out front. Now we're still going to list the coefficients. Okay, so we got our placeholder here, so constant, linear, quadratic, cubic. Now we do it starts pretty much the same way. We're going to bring the 1 down. I'm going to multiply, so this will be negative 2 times 1, which will give me negative 2. But in this case, what I do, because I carried the same number through that I'm seeing here, I see x minus 2 and I put a negative 2 here, this time the operation is subtraction. So 7 minus negative 2 is 9. Multiply by negative 2, we get negative 18. Negative 3 minus negative 18 is going to be 15. Negative 2 times 15 is negative 30. 4 minus negative 30 will be 34. And then again, there's my remainder. And notice it's the exact same thing. My quotient is still x squared plus 9x plus 15. And again, I know that because I know that each number here represents the coefficient of the term, and then increasing powers as we go to the left. So constant, linear, quadratic, once again. There you go. Doesn't really matter which way you choose to do this. If you change the value of the number, and I suspect a lot of you will like that method because you're used to doing that. Every time you've solved a quadratic, you did that. You changed the sign there, right? And then you add. If you just grab the number and plug it down there, the one that you see there in the binomial, then you subtract.
4x cubed minus x plus 3 divided by x plus 1.
Okay, so we're going to move a little bit more quickly through this one. I'm going to do it the two different ways again here, just to illustrate and give you examples of both, but you do whatever you need to. So I see x plus 1 here. So in my head here, I'm thinking, okay, I'm going to put negative 1 out front. And then my coefficients here are 4. Notice that there's no squared term. Okay, I need to have a coefficient for the squared term. I need to have something filling that column, so I'm not accidentally squishing these in too much. So there's my cubic, quadratic, my linear, and constant. Okay, and then the procedure is this. Bring down the first number. Multiply. Add. multiply those two, I get 4, add, and I'll get 3. Multiply, and I get negative 3, add, and you get 0. Okay, so my remainder is 0. My quotient is going to end up being, okay, here's my constant linear quadratic, so 4x squared minus 4x plus 3. Now, my remainder was 0. Let's just think about that. What does that mean? If the remainder is 0, oh, this means, so therefore, x plus 1 is a factor of 4x cubed minus x plus 3. Yeah, it's a perfect factor. Now, we're going to take a quick look at this again. This time I'm going to take and put positive 1 out front because that's the number that I'm seeing in the binomial. I still have to do the placeholder minus 1 plus 3. Again, if you're going to just grab that number there, okay, then I have to do, I set it up the same way, but I'm going to do the opposite operation here in a second. 1 times 4 is 4, and now I'm going to subtract. 0 minus 4 is negative 4. Multiply, get negative 4. Negative 1 minus negative 4 will be positive 3. Multiply, subtract, and again there's my remainder. And so again here, I interpret it the exact same way, 4x squared minus 4x plus 3. There you go. Same answer regardless of the method you choose.
3x cubed plus x squared plus 1 divided by x plus 2.
All right, do this one more time, both ways here. Now, again, remember what I've been saying here is that I'm showing you two different methods. You just got to pick one. You're not going to be asked to show one method or the other. You just have to pick one and run with it. So again, when I see this, I'm dividing this polynomial by this binomial here. I'm going to put negative 2 out front, okay, as my first method here, and then I'm going to put numbers here that are placeholders for each of these terms. Now notice it's a cubic. Quadratic, okay, I'm missing the linear term here. So there should be a 3 here, a 1 for the quadratic. There should be a 0 for the linear term that's missing, and then a 1 for the constant. And now my procedure begins. Bring down the 3, multiply by negative 2. So this is going to be negative 6 right here. And then add. So 1 and negative 6 will be negative 5. Negative 2 times negative 5 is going to be positive 10. Add. Multiply, so you get negative 20. And add, and you'll get negative 19. There's my remainder. And so my quotient, and again, look at what I'm looking at here. I was dividing a cubic by a monomial, that linear. I should be getting a quadratic, and that's what I'm getting. 3x squared minus 5x plus 10, and my remainder was negative 19. Now, let's try it the other way. Dividing by x plus 2, let's put a plus 2 outside. Again, the coefficients that go along here are going to be exactly the same. Still need a placeholder for the linear term. Bring down the 3, multiply. Whoops. Whoa, that was weird. 2 times 3, everybody, is 6. It's 6, always been 6. Okay, and now subtract, and we're going to get negative 5. Multiply, we get negative 10. Subtract, 0 minus negative 10 will be positive 10. 2 times 10 is 20. 1 minus 20 is negative 19, and there it is again. There's my remainder. And once again, my quotient is 3x squared minus 5x plus 10. Oops, sorry, couldn't see that. There you go.
Explore what happens when each of the above polynomials is evaluated for each of the following x values.
Okay, this is one of those questions that has a very, very specific point to it, and we hope that it makes sense to you. So what we're going to do here is explore what happens when each of the polynomials is evaluated at the x value that we're given here. So what we mean by this, what the question is specifically asking here is we're going to go back up to the previous question, and we're going to take in this polynomial right here, this x cubed plus 7x squared minus 3x plus 4, we're going to let x equal 2. So this is going to be 2 cubed plus 7 times 2 squared minus 3 times 2 plus 4. Okay, so now let's just go to the calculator. This is going to be 2 cubed plus 7 times, times 2 squared minus 3 times 2, oh, sorry, shoot, I hate when I do that. 2 squared minus 3 times 2 plus 4. And I got 34. Well, now, isn't that interesting? Isn't that interesting? 2 is the number that would make my divisor equal to 0. 34 was the remainder. Look at that. Isn't that interesting? What a coincidence. Let's take a look at the next one. X equals negative 1. So now in this case here, the polynomial is 4x cubed minus x plus 3. Okay, so here we go. So that's the one we're going to evaluate. We're going to plug that in. So 4 times negative 1 cubed minus negative 1 plus 3. Now, 4 times, okay, negative 1 cubed is negative 1. So this is going to be negative 1 times 4, negative 4, plus 1 plus 3. Our answer is 0. Well, would you look at that? Negative 1, negative 1. If you plug negative 1 into this, the divisor goes to 0. Huh. And look at that. The remainder was 0. Crazy. Isn't that interesting? Let's take a look at this next one. X is equal to negative 2. Our polynomial here was 3x cubed plus x squared plus 1. So here we go. We're going to plug negative 2 into that. So 3 times negative 2 cubed plus negative 2 squared plus 1. Okay, negative 2, well, okay, negative 2 cubed is going to be negative 24. That's right. I'm sorry, I'm anticipating the answer. Negative 2 cubed is negative 8 times 3 is negative 24 plus negative 2 squared is 4 plus 1. Negative 24 plus 5 is equal to negative 19. Well, once again, isn't this interesting? Negative 2 is the number that makes the divisor equal to 0. Negative 19 is the remainder when I divided by that. So if I bring that over, this is so interesting. If I bring this over and get x plus 2 equal to 0, okay, go forward. If I plug that number into that polynomial, I get the remainder when I divide by this polynomial. When I divided, now watch this, bring the negative 1 over. When I divided by this binomial, I got the same remainder. Bring this 2 over, x minus 2 equals 0. If I divide the polynomial by this binomial, I get that remainder. Isn't that interesting? Isn't that interesting?
And now we will introduce the remainder theorem.
And that that rule has a name, and again, like you just heard, it's the remainder theorem. So when you've got a polynomial, okay, and you're dividing it by x minus a, you can determine what the remainder is by doing something really, really simple here. All you got to do is take that value of a and plug it in. Now, the reason that works is because of the division statement, okay? So P of x, if we go back to this, P of x is equal to the divisor times the quotient plus the remainder. Now, we just looked at that a little while ago here. Now, watch. If we replace x with a, okay, the number that makes this equal to 0, if we replace x with a, you get P of a is equal to, well, now, what will a minus a be? If I plug a in here, P of a is going to equal a minus a times q of a. Well, it doesn't matter what q of a is. A minus a goes to 0. This whole thing would go away, and you'd simply be left with your remainder at a. The whole thing drops down to the remainder. That's the essence of the remainder theorem. Now, the reason why that's significant is because of what we're going to do with it in a little bit. Remember that our goal here is to give you a tool that will help you factor. Well, think back to this previous question here. Okay, I knew that x plus 1 was a factor of this because the remainder was 0. So now, what we're doing is we're giving you guys a tool for investigating the remainder without having to do the division. I don't need to do the division to know that what I'm looking for, what this little binomial is, I can determine whether it's a factor or not without going through all that work of dividing. That's great. Okay, that's a great little tool here. And now we're going to look at a few questions here where we actually apply that. And you'll see some different variations on how this gets applied.
Use the remainder theorem to determine the remainder of each of the following. Check using synthetic or long division. What does the remainder mean in relation to the graph of the polynomial function? The polynomial is x cubed plus 4x squared plus x minus 6, and we're going to divide it by x plus 1.
Okay, well, we're being asked to do a lot in this question, but first of all, we're being asked to figure out what the remainder is. I'm dividing by x plus 1. Okay, so I got to think, what number would make this equal to 0? Okay, well, that's equal to 0. Bring that over, x equals negative 1. So my remainder should be this polynomial evaluated at negative 1. Now, I can actually do this relatively quickly here because if I'm plugging in negative 1, it's pretty quick and easy. Negative 1 cubed is negative 1. Negative 1 squared is 1 times 4 is 4. Okay, well, negative 1 minus 6. And so what am I going to get here? I'm going to get negative 1 plus 4 is going to be 3. Minus 1 is going to be 2. Minus 6 is going to be negative 4. Okay, so there's my remainder. Now I can verify this using polynomial long division or synthetic division. And I tell you what, for this first one here, I'll use polynomial long division. Okay, you should be familiar with both methods here, but let's do this. So x plus 1 will go into x cubed plus 4x squared plus x minus 6. Now this is good because every term that I need is there. I look at the x cubed, that's the first thing I want to get rid of. I've got an x to do it with, so I'm going to multiply this by x squared. Just an x squared. I distribute this to both terms in the divisor. So x cubed plus x squared, and then you subtract. So the x cubes go away, that's exactly what I wanted, and then I got 4x squared minus x squared, so 3x squared. And then bring down the x and the negative 6. I start again. 3x squared, and there's an x there, so I'm going to have to multiply that by 3x. So 3x squared plus 3x. Subtract. The higher degree terms go away, and I know they will, because this is why I'm doing it. That's why I made those choices, to get rid of that. X minus 3x will be negative 2x minus 6. And now, to get rid of this negative 2x term, I'm going to multiply this by negative 2. So negative 2x minus 2, negative 2x minus 2, okay, negative 6, the negative 2x goes away, I knew it would. Negative 6 minus negative 2 is going to be negative 4. So there's my remainder, which is exactly what I determined up here. So that does work. Now, because the remainder is negative 4, therefore, x plus 1 is not a factor. Okay, it can't be. It can't be. If you're getting a remainder that's not 0, then that binomial is just not a factor of that particular polynomial.
The polynomial is 11x minus 4x cubed minus 7, and we're going to divide it by x minus 3.
All right, this is the same question, but when we do this one here, we're going to use synthetic division, I think, this time. So I'm dividing by x minus 3. Now think about what number I'm going to plug into this. If this was equal to 0, solve for that, I'm going to get 3. Okay, if I plug 3 into my polynomial, that'll give me my remainder. So this will be p at 3. So that's going to be, okay, I'll do some pieces here. 11 times 3 is going to be 33. 3 cubed is 27, and 4 times 27 is 108, minus 7. So 33 minus 108 minus 7 is equal to negative 82. All right, so there's my remainder. At least that should be my remainder. Now I'm going to double check that using synthetic division. I'm not going to do synthetic division twice here. I'm just going to use the first method that I showed you. So I'm going to grab that 3. Okay, the value that makes the that makes the divisor equal to 0. And now I'm going to put the coefficients down here for my dividend, but I got to do it in order. Okay, man, I don't like the way that's written at all. I'm going to pull that negative 4x cubed up front, negative 4x cubed. There is no squared term, so I'm going to put a 0x squared, then plus the linear term minus 7. So this is the order that I want to write this in. That's way prettier than the dividend that they gave us there. So this will be negative 4, 0, 11, negative 7. I can see that this is cubic because this is constant, linear, quadratic, cubic. That's all I needed. So now, bring down the negative 4, multiply, so 3 times negative 4 will be negative 12, and then add. 0, negative 12, negative 12. 3 times negative 12 is going to be negative 36. Okay, negative 36 plus 11 is going to be negative 25. And then 3 times negative 25 is going to be negative 75. Whoops. Sorry, I don't know why I did that. Okay, and then when I add that, negative 7 minus 75, negative 82. And that's exactly what I found. So that remainder theorem, man, that works. This is a much quicker way of getting that. Now, because the remainder here is negative 82, once again, we know that therefore x minus 3 is not a factor, okay, of the polynomial. Maybe I should say it like this, of p of x. Okay, not a factor of the dividend.
Determine the value of k if the polynomial is defined to be 2x cubed minus 5x squared minus 4x plus k, and there is a remainder of negative 2 when the polynomial is divided by x plus 1.
Okay, now I hope people choose to use the tool here that we're giving you, the remainder theorem, to answer this problem. I oftentimes, when I work through this with people here, I see people want to just do division. They just want to do the division and okay, we're going to divide, sorry, what are we dividing by? In this case, x plus 1. And they'll just fight with it with that k in there and then equate the answer at the end to the remainder and whatever. This is so much easier just to use the remainder theorem. It really, really is. Okay, we know, because I'm dividing by x plus 1 right here, if I set this equal to 0, I know that if I plug negative 1 into that polynomial, okay, that if I plug negative 1 in, my result should be the remainder, which in this case is negative 1. That means, okay, if I make sure I can see the polynomial here, if I plug this in, if I plug in negative 1 into this, now negative 1 cubed is going to be negative 1, times 2 is going to be negative 2. Negative 1 squared is going to be 1 times negative 5 will be negative 5. Negative 4 times negative 1 will be positive 4. Plus k, that should equal negative 2. Now, just bring everything over. Negative 2 minus 5 is going to be negative 7. Plus 4 is negative 3. Bring that over. By adding it, I get k is equal to 1. That's it. See, it becomes a really easy little equation to solve if you use the remainder theorem. Okay, I'm dividing by this binomial, so I know that if I plug in the value that makes this equal to 0 into this, I get that. Beautiful, beautiful, quick little equation, easy to solve.
For what value of m will the polynomial p of x equals x cubed plus 6x squared plus mx minus 4 have the same remainder when it is divided by x minus 1 and x plus 2?
Okay, now this is a very similar sort of problem, except in this particular case here, we're not told what the remainder is, but we're told the remainder is the same. Now, I might not know exactly what the remainder is when I divide by x minus 1, but I do know that it will look like this. That if I take 1, the number that makes a 0, and plug it in, this is the remainder. I don't know exactly what the remainder is when I divide by x plus 2, but I do know that that remainder will be the same as evaluating the polynomial at negative 2. And this question here tells me that these two are equal to each other. So this is what gives me the equation to solve. Now here's my polynomial right here. Okay, so now I'm just going to plug 1 into that. Now 1 cubed is just going to be 1. 1 squared is 1 times 6 is 6. M times 1 is just going to be m, and then negative 4 is, well, just negative 4. I'm not doing anything with that. Plug negative 2 into that. Now negative 2 cubed is going to be negative 8. Negative 2 squared will be positive 4 times 6 is 24. M times negative 2 is going to be negative 2m, and then minus 4. Okay, now I just want to get the m's together. I've got an equation in just one variable m. It's not even quadratic. It's just a linear, okay, on the m here. I know that the negative 4's are going to cancel here. I will bring this 2m over to the left-hand side to get 3m, and I'm going to bring everything else over. So 1 plus 6 is 7. Okay, so take that 7, bring it over. I'm going to get negative 15 plus 24. Okay, so negative 15 plus 24, just give it a couple seconds thought there. 9. And then when you divide, m is equal to 3. It's actually a very straightforward problem if you use the remainder theorem. Okay, and I know there's going to be a bunch of people that are going to want to do this using division, like polynomial long division or synthetic division, and then kind of have to play around with the remainders and set them equal to each other. I really strongly advise you to get comfortable with the remainder theorem.
The polynomial p of x equals 4x cubed plus bx squared minus cx plus 11 has a remainder of negative 7 when divided by x plus 2, and when evaluated at 1, the result is 14. Determine the values of b and c.
Okay, so this question here is a bit of a classic. You kind of need to do this problem when you start working with the remainder theorem. One of the reasons why this is a good problem here is because it kind of harkens back to work that you did a while ago, okay, when you started solving systems of equations. So what we're going to do here is use the remainder theorem to build a system, and then you'll use the system to solve for b and c. So let's just look at the information that we're given here. We've got that polynomial, and it has a remainder of negative 7 when divided by x plus 2. Now, okay, so if we let that equal to 0, solve for x equals negative 2. So if I plug negative 2 into the polynomial, I get a remainder of negative 7. Okay, so that means p at negative 2 is equal to negative 7. Okay, good. That's what that first little bit of information is. And then I tell you right up front, okay, p at 1 is equal to 14. All right. Okay, well that's that. P at 1 equals 14. But let's just take a quick look at and interpret this, see what this is saying here. When you plug a 1 into this, what we're saying here is that x equals 1, because there should be an x in there, but we put a 1 in there. Bring that 1 over, and we get x minus 1 is equal to 0. Now, think of the way the remainder theorem here works. What this means is that if you take p of x and divide it by x minus 1, the remainder is going to be 14. Whoops. I just want you to be clear on that. I want you to be able to go forwards here. If I give you the remainder and tell you what I'm dividing by, what the divisor is, I want you to be able to build this statement. But I also want you to be able to go backwards from this statement here to understand that I'm dividing what I'm dividing by, what the divisor is, and where the remainder fits. Okay, so now with that in mind, let's build the system. So if I plug negative 2 into my polynomial here, this is going to end up giving me negative 32 plus 4b plus 2c, sorry, no, that's right, 2c, my mistake, plus 11 equals negative 7. Okay, now I'm going to go to my calculator here because I have been known to screw this up a couple of times here. And so I'm going to have 7 equals 14. So there we go. So this will end up being 4b plus 2c. I'm going to add those two together, the negative 32 and the 11, and then bring that over, and I will get equals 14. And I'm kind of lazy here. I see everything's even, so I'm going to divide everything by 2 to get 2b plus c is equal to 7. All right, now I'm going to look at the next little bit of information here. P at 1 is equal to 14. So if you plug 1 into that, you're going to get 4 plus b minus c plus 11 equals 14. Okay, well, 4 and 11 is 15. Bring that over, so it'll be b minus c is equal to negative 1. Okay, now, here's my system. And like immediately when I look at this, I see a positive c here and a negative c here. So that means I can eliminate that variable by writing these equations over top of one another and then simply adding. All I got to do is add this down here. So 2b plus b is going to be 3b. Okay, the c's will cancel, and 7 and negative 1 is going to be 6. And so I can see right away b is equal to 2. And then with that, I can plug that back up into this equation, the second one. 2 minus c is equal to negative 1. I'll bring the c over, bring the negative 1 over, and I'm going to get that c is equal to 3. And there we go. That's what we were looking for in this problem, the values of b and c. We used the remainder theorem to create the system when there was two unknowns in the equation, in the polynomial. And then I solved the system using tools from way back. B is equal to 2, C is equal to 3.